Hi, Honors and Comp. Mrs. KJ here, going over the lab about solubility. It is possible to alter the dissolution rate in the laboratory. So dissolution means what? Dissolving. Rate means how fast. Several factors affect a substance's rate of dissolving or dissolution rate. In this lab exercise, you will alter factors as you create solutions. You will then identify a solute based on when it precipitates out a solution. You will also apply the concept of collision theory to understand the significance of your results. Factors such as temperature and surface area can influence the rate of solution formation. Temperature and surface area can influence the rate at which a solute, what's being dissolved, dissolves. This concept may seem easy to understand, but it's an important one for chemists who need to characterize the relationship between temperature and dissolution and between particle size and dissolution in many types of lab procedures. Look at the picture of salt dissolving in water. The temperature of the water and the surface area of the salt crystals influence the rate at which the salt dissolves. So, for example, salt is NaCl. Sugar is C6H12O6. They're going to have a different dissolving rate based on how big they are. The smaller they are, the faster they're going to dissolve. The more surface area something has, if they were the same size, then the faster it's going to dissolve. The knowledge that dissolution can be explained in terms of particle collisions is called collision theory. This theory states that the particles that make up any solute or solvent are in constant motion. When the solvent, what's doing the dissolving, like in this case the water, particles collide with solute particles, like the table salt, dissolution is the result. In this lab, you will investigate the effect that changes in temperature have on the rate of dissolving. Then you will use data that you have collected to identify an unknown solute. The key component of identifying the unknown will be the graphs you make, commonly called solubility curves. All right, so then we're going to go back up to the top. And when you get this form, here's the link to do the lab. Define dissolution. A solution is saturated when. What can you do to a solution to increase saturation level? Use your knowledge of atoms and molecules and of the kinetic theory to explain why things dissolve in terms of collision theory. Hint, start by defining collision theory. Be sure to cite your source if you copy the definition. And that's true for any of these. Always cite your source if you copy something. Solubility, the phenomenon of dissolution of solute in a solvent to give a homogeneous system, is one of the important parameters to achieve desired concentration of drug in systemic circulation for desired anticipated pharmacological responses. So in other words, it's important when you take medicine. Low aqueous solubility. So the fact that it's not going to dissolve real well in water is a major problem encountered with formulation development of new chemical entities, as well as for the generic development. So you hear of generic drugs, they're a little bit different. Well, they have to make sure that they can dissolve well enough for the body to actually make it worthwhile. More than 40% of new chemical entities developed in a pharmaceutical industry are practically insoluble in water. Solubility is a major challenge for formulation scientists. Any drug to be absorbed must be present in the form of solution at the site of absorption. In other words, it needs to dissolve in water so your cells can use it. Why do we need chemicals to be soluble? What could scientists do to combat this problem? So you might have to come back and think about that one. All right, so we're going to use the data stations from part 1 and 2 to complete the data table, and then we're going to make a graph. So how you are going to do this, I zoomed in so we could see what's going on. The first thing you're going to want to do is you're going to take the temperature, and you're going to repeat this for B, C, and D, and then you're going to repeat all of this. Here we're doing it for KCl. You are going to repeat it for KClO3. All right. So our temperature for beaker A is 4.9. So, oh, we're doing KCl. So, oops. Got a little typo there. There we go. 4.9. And over here on this one, there we go. All right, and then we need to know the amount of KCl at saturation. So what does saturation mean? It means that no more will dissolve. Okay, now they have a 1 gram scoop, and a 5 gram scoop. We're going to use the 5 because we're going to get the same results, and it's just not worth the time to sit and do one at a time. So you click to get a scoop, you click to put it in, you click to get your spoon down on the table. See this white down here? That means it's not dissolved. You have to stir. If it disappears, that means more can be dissolved. If no more can dissolve, then it means the solution is saturated. And we found the saturation point, or at least close enough as we're going by fives, and we can record our data. So I'm putting in my third scoop, which would equal 15. And again, make sure that you are stirring after every one. And again, we're going to continue until it's saturated. That's my fourth scoop. And I'm looking at the bottom to see if there is white that settles on the bottom. Like if you've ever made Jell-O, you know that if it's not hot enough, or you don't stir it enough, or there's not enough water, you know that it's saturated and you have the leftover on the edges and the bottom. All right, so I'm up to scoop number 6. And there we go, it is saturated. I know it's saturated because I can still see it on the bottom. We're going to change our temperature to 5.6 because it did increase temperature and that does make a difference. So we're going to change that to 5.6 and we put in 6 scoops. 6 times 5 is 30 grams. Now, our next one, beaker B, same thing, we're going to get the temperature. You can leave it right on the burner to keep it at a temperature. Now, how many scoops can I start with in here? It's at a warmer temperature. So is more the same amount or less going to dissolve? More should dissolve. So I can actually start with 6 scoops. I don't have to keep doing it one at a time because I know when it was colder, 6 scoops dissolved. So now that it's warmer, the molecules are moving faster, there are more collisions. I know that I'm going to be able to dissolve at least 6 scoops or 30 grams. And so I can put 6 in and stir it, and woohoo, it's all gone. And then I can keep going from there. So you can use that for this set of beakers, okay? But remember, when you get to the other set of beakers, you are going to have a different chemical. So you're going to have to start over with 1 scoop at a time in beaker A. So it helps if you go from A to D because it goes from coldest to warmest. All right, so that's the first part. You're going to get your data and you are going to plot your points. Now, you need to make a best fit line for each set of data. That means have blue data, which is the KCl, have your purple data, KClO3, and then you're going to make a best fit line for each. Now, reminder about best fit lines. Best fit lines do not need to go through the origin. Okay, they can, but they don't have to. So if this is my graph and I have my blue data, let's say it looks like this. My best fit line is a straight line that goes through as many points as possible with the same number of points above and below. This is not a good best fit line because all my points are above it. That's not good. We want it to be balanced, kind of like a teeter-totter. All right, so let's try this. If I do this, now I can see I have 1, 2 above and 2 below. That part is balanced. However, notice this. If I look at how far away they are, you can see that overall, there's a bigger distance on the bottom compared to the top. So that is also not the best fit line. All right, let's try it again. So again, your best fit line should go through as many points as possible. And I would say it would be somewhere like that. So I have pretty much equal distance overall between the top and the ones that are below, and 2 are above and 2 are below. Notice how it does not go through the origin. That is okay. So you'll have 1 set of data and a best fit line for your blue points, and then you will have a different best fit line for your other set of data. So again, it might go through the origin. Your best fit line might go through the origin, and if it does, that's okay, but chances are it won't. And we want to get it nice and balanced. If we can get it to touch all the points, that's the best. And I would say that that one's pretty good. So it's balanced. All right. Then the last part you need to do, you're going to have to put on points A, which will be a green point, and point for beaker B, which is an orange point. And that's your data from down here. So this one is different. We're going to go to station 3. I would actually suggest doing this right away because this takes a while. Here they're already heated, and we're working backwards. They're already heated to exactly 80 degrees Celsius. And we want to let them cool down. That means you have to take them off of the burner, and you'll notice the temperature will decrease. When it gets to the point where it's too cold to have everything dissolved, the solute's going to come out of solution. And what that means is it will look like snowflakes on the edge, and that's the temperature you need to write down. Okay, so it'll look like crystallization or condensation or snowflakes on the beaker. That means that the solute is coming out of solution. In other words, it's too cold for all of it to be dissolved. Beaker A has 32 grams. Beaker B has 37 grams in it. You are going to write down those points. So 32 grams, you're going to tell me the temperature that you saw the snowflakes, when you saw the chemical come out of solution. The same thing for beaker B. Then plot these points, 32 in this temperature, 37 in this temperature on the graph above, and tell me, is it KCl or KClO3 based on which best fit line is the closest to your dot? So you must mark both points on both graphs and explain which substance is which. So this is KCl because it was closer to the blue KCl best fit line. That's what I want. Or if it's the other one. Using your data, state the relationship between temperature and solubility and why that is true. So in other words, why when temperature goes up, solubility goes blank, why? Using your data, so I need numbers in your answer from above, probably from parts 1 and 2. Compare the solubility of each substance tested and why that is true. So there must be data in your answer. I suggest comparing a point on the graph that has the same temperature. So if they both have a point at 40, say, oh, KCl dissolved 50 and KClO3 dissolved 60 grams. And the reason why KClO3 dissolved more is blah, blah, blah. And it does have to do with size of the molecule. So if you need to, find some information on that. Okay, when you're done, you can submit it.